Hey everyone, thanks for tuning in here. Give us just a moment. I am muted in the Discord chat, but we are going to be having an open discussion tonight about constants within physics. So once Alan unmutes, I will also unmute, and I'll do a more proper introduction here. But I figured instead of leaving y'all hanging, give everyone a couple of minutes to come into the stream if you wanted to, and if you wanted to maybe catch some banter before we were initially going to go live here. But yeah, thanks for being with us and stay on standby. I apologize in advance for any dead air, but just the nature of starting the show sometimes. You can always skip ahead if you're listening later.
All right, sorry about that. I ran a little extended intro, but we are live now, gentlemen.
Excellent. Oh, hold on. Excellent. Well, thank you everyone for being here for Æther Round Table number 44 on the constants in physics that we're going to take a re-examination of or deconstruct a bit of them as well, and just Alan's going to do a bit of a small presentation, I believe, or kind of guide to discussion, and then we'll open up the floor for open questions, comments, thoughts, and perhaps more people will file in here. If not, I guess five's a company, five's a party, we'll say. So we'll figure it out as we go. But in any case, thank you everyone for being here. And Alan, I don't know if you had anything you wanted to open up with particularly here, but you want to
Yeah,
go for it.
so to start us off, if we open up our thing, I should open this ahead of time, but what's the oh man, should open that ahead of time. But anyway, if you open up any physics book, you'll have a table. In the table of contents, you'll see, universal constants that they use, right? And it's like, what are these? Where did they come from? What are they used for? And, do they necessarily have to be an actual value that's associated with the physical mechanism to be used in measurements, if all measurements and everything based on a model or ratios of those constants, right? Because it's always going to be in some proportional relationship in that regard. So to kind of start us off, look at the electron, right? And how that's the model, the basis for, subatomic particles, for the whole model explaining the atomic, everything that happens on the atomic and subatomic level, right? Starting with the electron. And it's like, well, how'd they get that? What does it mean? Well, they started with introducing energy into a system and making measurements with what it would take to cause that energy to deviate from being in a straight line, essentially. So they introduce an electric and magnetic field to that system. It'll cause a deviation in that beam, and then from that, just making precise measurements and keeping it consistent with how much energy they can introduce versus how consistent they can repeat that measurement. They came up with the quantified amount that they would distribute over the radius of a sphere as the as the energy potential of that. And from that, they just made a little particle, right? And then as they build out from that constant, everything is a ratio of how many electrons are orbiting this nucleus, right? So that's how it all breaks down off of how you build off of a constant. Like the whole model and everything is built upon that. And then when they got into quantum field theory and quantum electrodynamics, when they started doing experimental verification of the accuracy of the physicality of the model that they put forward, well, they found that their predictions were off, and then they had to make new constants and adjust those and keep that going. And then that's where we got into the situation where they just kept refining things and adjusting the constants and doing expansion series to infinity to make everything fit this original measurement, to get it to circle back to that. So we're just kind of examine some more of these and break down the historicity of them. The big ones, of course, are the mass of the Earth and big G here, right? These are the equations that govern the cosmos. So we're going to be taking a look at those and how they all relate to, or how they're all in relation to one another, and what that means and what the implications are for just having a constant to have a baseline to jump off of, so to speak. So, all right. With that said, Shane, do you want to say anything?
Yeah, hold on, let me get my other stuff ready though. We'll go into, I think we gotta do little G first, because then that's used in big G, and then we
Do you
can do
have stuff to share for it?
yeah, that's why I said I gotta go
Okay.
look for it real quick. So give me like 2
Oh, gotcha.
seconds, then I'll be good.
Yep. No worries. No worries. Let's see if I can find that on the table of contents for that thing, so we can get a nice list going.
Nice. So we have the formula A equals 2h over t squared does not directly depend on the gravitational constant g, but rather gives you a way to calculate the acceleration from the distance of an object has fallen and the time it took to fall. If you want to calculate the acceleration g without using the universal gravitational constant of big G, you would typically perform an experiment where you would measure the time t it takes for an object to fall a known distance h, and then you would use the formula to solve for a. So if you drop an object from rest and measure the time it takes to hit the ground, you could calculate the acceleration using this formula. This method does not require g or the masses involved, only the distance fallen for the time it took. Shane posted here.
Yeah, that's the big G. But like, so yeah, big G is just a constant. It gets it's really an indirect inference of a margin of torsion, right? It's kind of crazy, but we'll get into little g first, because that's uses little g to derive big G, and big G is a constant. So little g is not a constant, right? Little g is usually an average, and we have 9.8 meters per second squared is typically. Wait, am I sharing something? Yeah, it's not on my stream. There we go. Wait a second. It's
What
not
we're
what I'm
seeing
sharing.
is the derivation for big G. Is
Yep.
that what
So I
you're
was like,
supposed
that's
to? Okay.
that's not what I
Okay.
meant to be sharing. Let's
Okay.
do. There we go. Hey, okay, cool. Hey, little g, cool. So it's not just the agreed upon average, meaning that usually 9.8 is that's the rate at the equator, right? So you get just as a function of height and time. The actual starting equation before you algebraically simplify it is height equals 1/2 acceleration times time squared plus velocity times time. Right? And then you break it down, it really just means to solve for little a, the acceleration towards the earth, so to speak, or I don't know what Dell would call that, the inverse, right? He says this doesn't exist, but the little a equals 2 times the height over the time squared. So to do an example of that, right? You can just put it in a real life situation and say that if you drop a ball at this height, right, takes 1.43 seconds, you drop it from 10 meters. Quickly do some math. 2 times 10 over 1.43 squared. 1.43 squared is 2.049. 20 divided by 2, 9.78, right? Pretty on the nose, right? So this is important because they use that for the big G, right? And again, it's not a measurement that they that they calculate there. It's a direct inference, which is the craziest thing I've heard so far. So what big G represents is a radial measurement of density per like square inch or whatever, per square metric, per square meter, whatever, right? That's what the constant is representing. So they inferred this constant by doing a Michelson-Morley and then invoking the torsion being the T equals FFD over here, right? Where force proportional to the mass is equal to,
Cavendish.
yeah.
Not you. You said Michelson Morley.
Did I? Holy crap. Cavendish.
Yeah.
Yeah, no, definitely Cavendish. And what was I gonna say? Oh, man, now I'm thinking Michelson Morley, but it's okay. So they have the torque force, right? By T over here, T equals K there, whatever. The other thing they do is they use the weight and mass formula and they interchange those around. Actually, hold on, let me go get those real quick. Actually, no, they're pretty easy. They're pretty easy. But like weight equals G, right? So they just use wherever a G appeared, and we'll just replace it with little a in those formulas. No big deal. But for the weight formula, they use that in here, and they use the weight and the torque to insinuate a constant, essentially, and they lightly infer it. So you set it up from right here, right? This is the Newton's gravitational equation, which for right now will allow to have mass in it because we're going to use it real quick. We're going to derive G from this, right? So distance between the centers of the masses, and then typical of the experiment, it's like those two lead balls, right? And then T is the torque between them. The measure looking downward, it's like stereographically looking down on the instrument. It'd be like the angle with which the thread is twisting, right? The amount that the ball tracks to the other ball as measured in twist, essentially, if you want to look at it like that.
Measured in ball twist, I think is the SI
Yeah,
unit.
essentially, yeah, it's ball twist, yeah, SI. So you go through here, you get to the next spot. Since you have this, T equals FD, and you have this for T of K, K of prime, you're solving for G. You just plug in these two masses over here, and you get you can infer your constant, right? Which is essentially just a measurement of the angle between the torsion, the radius between the distance between the two spheres, the radius between them, and our good old measure of torque. So gravitational constant derived from the overall pressure density of the Earth, right? And they're saying that they need little a, or they need G, right? The acceleration downward to work with the constant. So it's really just a function of little g, right? What do you think about that, Alan?
Big G is a function of little g.
Yeah. Yeah.
I mean,
Need it.
there's no other way to really look at it because they need the weight of that to even begin to even pretend to do anything from it.
Yep.
It's it's the only way to do it.
So what do you guys think about that before we plow forward? Big G, little g,
So
electron.
so in doing that, right now if one were to accept that, right, like let's look at the consequences that they're putting forward, because what they've discovered, with math and physics here in the early 1800s, 1700s, right, is that you need constants to do ratios of things together. So this is like presenting the narrative to the public, right, so to speak, because like all we have are these. You can go back to the Royal Society right now and read all about the documentation of Cavendish, dude, and this whole thing, like, in great detail, right? But it's the importance of it is getting you to accept this as is. So it's like, okay, what did we just do here? We just established the gravitational force there, and then we can also, with that, we can derive the mass of the Earth now, and now we can start doing things for astronomical observations where we can apply our constants and ratios to see if those match and then those will of course match the periodicity, because that's all it's ever been a function of. But this is how they slid everything in, getting you to accept this, because when you do like energy analysis and stuff, you need some constants to go off of, something, like, even if it's not true, it still has to be some value in there. And this is just like the story that they put forward is like, oh, we just happened to measure the Earth, dude. We measured the weight of it. We measured how much that gravitational force is.
Yeah, right. We've inferred it from all the things that we know are real, and now we're gonna tell you that it's all based on mass. Mass is the thing that they keep inserting to be the cause. Like, ever since Newton robbed Kepler, inverted the centrifugal force formula to give you the opposite force of gravity that only can ever exist in its position as a perfectly balanced force and in direct opposition to the very real equilibrium force. Like, so it only gets used when it's perfectly balanced and in opposition to a direct oppositional force called centrifugal force. So if you think about how it came about, right? If Newton inserted a reverse centrifugal force equation into Kepler's equation for periodicity and observation of celestial events to say that mass is actually what's moving everything in the sky around, and all all he did was take a known force and invert it to give us a pseudo force, and then said that actually that pseudo force only exists when in total opposition to this known force. So who's to say that the known force isn't doing all the forcing in the first place? You know what I mean? Kind of like it's a trick. It's the gravitational forces when applied to tides or masses or gravity, anything they're using it in, it's always in direct equilibrium to centrifugal force. So much so that if you're a glober, you might yell at us on one of our videos and say, gravitational, it is the centrifugal force, you idiot. And that's at the point where it is, because they're almost synonymous with them. That's what Bennett pulled his paper down for on the tidal forces, because he made that little mistake and treated them differently, even though in the math they're the same because it's a balanced equation and it works out completely the same. But because he forgot to differentiated them and forgot that in their model they're synonymous. Of course, he knows that they're not synonymous because he understands, right? But it only exists when it's in complete mathematical equilibrium to an opposing force that negates it. What do you guys think about that bit before we go forward?
The one trick they never tell you about.
I really figured that out in tides when I was doing tidal forces stuff to figure out how the moon isn't moving anything around with gravity forces, and how they said that it has like constructive interference when it gets next to the sun, and they treat waves like gravity, and that constructive waves, positively increase it and destructively would slow it down. But anyway, that can't happen because it only exists in a centrifugal force, and the sun's centrifugal force is much larger than the moon. But that's a whole different presentation. I just noticed that they only use the gravitational force when it's completely balanced by the centrifugal force, and that's like a neat math trick. It's almost as if it was never there at all, guys.
Shane, can I ask a quick question? So backwards engineered is the theme here, right? So the inference goes from A is substituted with little g, so we know the acceleration, and based on the torque of Cavendish, we can derive a constant based on the mass of the torque of the mass of the two balls going that. Is that how they guesstimate the mass of the Earth being they'll assign that same rate of acceleration to celestial bodies, and from there they guesstimate a mass, if you get what I'm growing at?
Well, it's close, right? The only way they get mass of anything in the sky is Newton's. Actually, let's just go to the database real quick. Let me just.
Yay. Big
Hey, what's up,
G.
Ezo?
What's up? Finishing my last homework section.
Nice. Do you got some time tonight? Because we want to talk about the ether density thing you showed us earlier.
Oh, I was
That's
just gonna. I didn't realize how busy you guys were. I was gonna drop by and say that the mainstream, if you wanted to like discuss it with mainstream people so they didn't get all butt hurt, at least to get them to listen and share data with you, you could say, well, because of mass energy equivalence, it's not that you're actually measuring a mass density, but it's the energy density equivalent to mass of the quantum vacuum through which the light propagates.
Nice.
Yeah.
Just to grease the axle.
Yeah.
So, first of all, right, you have Newton's law of gravitation being imposed and derived from Kepler's law. We talk about this constantly. I'm not going to spend a whole bunch of time on it. Now we can go through it if you want. Alan has a wonderful visual on the cube representation. We can walk through if anyone wants to. But once you have this right here is what we're going to use to derive constants. And as far as getting masses, you only can get masses of stellar objects by this neat algebraic trick by assuming this and then inserting it back in. So when you get a simplified version, find it soon. There we
That
go.
was a really cool graphic, Alan. That was good. We need graphics like that.
Right here. So right here is this Newton's law, right? Is the only way they can guesstimate. So this is what he used in various forms to get masses of all cosmos. Without this, nobody knows the mass of any damn thing. Right? If you without this breakdown on this and this right here, which is what we use later, then no one knows the mass of anything. So what they use to infer the mass of the Earth is a combination of the g, the little g, the torsion that we just used, and the the periodicity of Earth, right? The sidereal time, essentially, which is what I was showing before, which we can get into real quick. So, actually, yeah, let's do that. All right, this isn't a formal presentation. We're kind of hopping all around, but give me 1 sec.
Take your time, boss.
Could be a formal presentation. We got most of it ready. Back to this boy. All right, so there, yeah.
Nice.
So the mass of Earth is a completely arbitrary derivative of the constant g when applied to masses, right? That's how they got it. So it's not really a real thing. That's how, when you apply it to anything, as in like Kepler's law, we can always drop it out and it becomes useless. The mass, as we always say, lads, blinks away, right? Goes away, disappears, cancels right out. No mass. Where's the mass meow? It's gone. It's been gone.
Yeah.
Now, the last thing I think, because this is where it gets a little bit tricky, is where they get the AU. Unless you have anything else, Alan, before we go into that.
No, man. No. Xavier, do you need anything else on that?
No, I got it. It pretty much is A plus the periodicity of celestial bodies to derive something. Got it, though. Thank you.
Yep. Cool. So yeah, let's get into the deriving the AU, because this is all going to be a function of how everything scales, and everything has to be proportional. Like we talk about scale invariance a lot and proportionality for periodicity. Well, this is going to be how they derive this from optics, from using constants in optics.
Yeah, the way it ties in really is sweet. Like it's nicely put all this in a nice neat circle. So they're like, oh, the distance to the sun is a heliocentric exclusive thing. We know it for sure. It definitely is no, it's based off the, first of all, observations from the Earth, right, of the sun. And in typical, it's optical diameter. We're not going to get that year, but in this case, we're just going to use the sidereal time, and we're going to compare it to a different sidereal time. So we're going to take an object in the sky. We're going to mark its periodicity. We're going to use that. We're going to mark it against the periodicity of the overall background. That's all Kepler's law is gonna show us, right? So the ratio of distances is how we get it. We don't know what this is. We're just gonna get a ratio, right? So this is what ends up being when you do the math. And then you bring it over to the proportionality deduced by the derivation of Kepler's law, which is the major period of this periodicity with the major of the semi-axis. So you use this axis or this ratio over here, and you do this to the third, and you get this final constant. So we know in this case, they're going to use the comparison to a different astronomical unit, but in their historicity, I think it was Mercury, and they just assumed, right? And they just say, oh, it's a 1-for-1 comparison. So that's what this part is. If you use Venus, it's 1-7.2, but that's assuming that you know what it is. But they just assumed it was 1-for-1. They went, ooh, we're gonna figure this out based on a known ratio of something we're gonna totally make up and assume right now. Oh, it's like in math, right? When you're using ratios and measurements, you're like, oh, I can do that if I know it's a known ratio. And for this known ratio, someone took a guess. They were like, yeah, it's probably about right. And then later, with backwards compatible math, they were like, oh, you know what? You were exactly correct. It's 1.00. Anyway, moving on to this math over here. We have continuation. This is actually the square root of 3 times the square root of 2 times the constant equaling this. So we have the orbital periods of Earth and Venus, just getting Earth, just using Kepler's third law. We can estimate the AU distance, which is, of course, the distance from the Earth to the sun, which they're going to use and compute as 1 AU to mark and delimitate distances going forward. But it is the Earth-Sun distance. And it just uses orbital periods and distances. So they use that ratio, they compute it, they get, well, 0.99 astronomical units. But that's just with this ratio. So they would just assume that, and they would know exactly, oh, if you actually do the conversion to meters, it gets to 93 million miles is what it comes down to. Now that's not what they claim to have done, right? This is what they claim to have done. They claim to have used the solar parallax angle. Now, again, if you haven't looked into solar or parallax at all, Alan's got a wonderful presentation on it. We have a list on it. It is absurdly small angles that they're dealing with, first of all, to do anything and then make inferences of. Plus, in the case of reality, stellar parallax goes, 46% in the other direction. So if you're using it to imply a Earth motion, Earth's moving halfway in both directions at once or whatever. So that's a little bit different. But if we're going to use they said that they use parallax to compute the distance to the sun. So someone took an angle of a star and went, ooh, that tells me in miles how far away the sun is. No joke. This is real history, guys. Let's just put a disclaimer. This is what heliocentrists actually believe. Okay. So we do a little bit of math. We just get the angle. We'll call it, this one we'll do the angle in degrees conversion to radians to get our actual starting measurement. So the next slide is where it continues. This one. It's funny, right? Because what Alan said about converting it back to optics means that this doesn't work. None of this works without the radius of the Earth. You can't have it without the radius of the Earth, right? And we know the radius of the Earth is derived from optics based on angular resolution limits and distance to the horizon, based on regular wavelengths and a 6-foot observer. Right? But that's, again, a different presentation. We'll get back to that. But just know that this doesn't go forward without this value. So they use parallax distance measurements. They assume the radius of this. They plug in the radius. They use the proportionality of Kepler's third law again to work out the math to calculate to yield. Oh, look, actually, it turns out it's right where we found it, 93 million miles, just where we assumed it. And the other part of that is the people of history. There we go. The people throughout history, right, who had guessed at the distance to the sun was just manipulating a optical diameter formula. Remember when we always say, you know, angular size formula? In fact, Reg Rhetoric, our boy, shouted this formula out at me in anger over some unrelated things about Polaris. But I guess he wanted everyone to know that he knew it. And to be fair, it's a good formula, right? We scooped it up immediately. Thanks, Red. Now we know exactly what all this meant, right? When Copernicus estimated the sun was 3 million miles away, it's like, well, how did he do that? Well, if you assume that the sun is 0.53 degrees, meaning that it appears to be just about, you know, if you put your thumb on it, it's about that big. It's a measurement of the optical diameter of the solar disk, right? That's what that is. If you assume that it's, you know, say 322,000 miles away, then it's, you know, 3 million miles wide. He's assuming it's a huge sun and it's 322,000 miles away. All of these would work for this apparent 0.53 degrees. So by manipulating this formula, right, you can see that he got this. Now, by the end of this, you get really, really close in 95, 104. But the only thing that's changing in this is the manipulation of the distance and the diameter, because we know the optical disk doesn't change, but actual size of the sun, diameter in miles, and the distance to the sun in miles. Those are the two components that are being manipulated in this formula for D over 2 times D, right? Because you got the little d distance to the sun, big D with the diameter of the sun in this case, right? So these people are manipulating a backwards engineered constant to say, oh, look, we know for sure based on stellar parallax angles and not based on this formula at all that the sun is 93 million miles away. And if you look, I did all the calculations here.
When you get a chance, though, swap up the headings of columns 2 and 3.
Yeah. Right. Distance and diameter for sure. This would definitely be the distance. And this is the diameter. But essentially, it's all just these people, this meme, right? People like, oh, we were only getting more accurate. And it's like, well, that's not true either. But the other part is you're just manipulating what you think the distance to the sun could be based on the diameter, right? And once you get one right, it shifts proportionally. So that's the other portion of the constants. And I think we have Planck's constants to go into if you want a little bit. And then Piezo gave us the metric to determining the density of the etheric background.
Dude, well, Piezo's AFK. So, does anyone have any questions about what we just went over so far? Any thoughts?
Yeah, how do they determine the diameter of the sun? I was paying attention, maybe I didn't understand.
Oh, right here, and they make wild guesses until it works. Yeah.
Okay.
Yeah. Because of the covariant scaling factor, they know that this is the true observation of the sun size. So the other two fucking willy-nilly play around with, doesn't matter. Like, so you just find the proportionate covariant scaling pair that matches with this, and wouldn't you know, this is where it gets 93 million miles and 864,000 kilometers wide, happens to fit perfectly or something, right?
So you assume
So-
one to get the other? Is that basically it?
Yep. This
Yeah, so remember they had a distance already, from Kepler's laws for from the astronomical unit. So now the task was just to make the the apparent size, you see the angular size match the, a distance proportional that would give you the actual, quote unquote diameter of the sun, right? So that's where that's how it's all derived.
Got it. All right, thank you.
Or what they assume to be the actual diameter, but it just fits with the periodicity, right? So then, they further built upon that. That's why when it got to Ergo, Aries failure, Michelson-Morley, that's why those things were so significant, because these constants that they had built their worldview on, that they had built their model, their cosmological model on, were being tested, and they were false. But yet their math still described things. So it's like, obviously the things were happening independent of their math, and they were just refining the math to meet the observation. But look at all but in between that period of time, look at all the power and virtue that they harvested over, progressing science and figuring out, based on the mass of the earth and all this stuff, that, it was just too much to let go. Once you have that, like, how can you're going to give it
Can you
up,
not
right?
abuse it to control the whole world and manslave the minds of millions? Of course you would.
Just
I
keep
guess.
using hot glue on the house of cards.
Yeah.
Well, planks. We're going to planks.
And then
Planks.
keep in mind this, this scale only applies to like the solar system as we see it, right? Where they get into things like the Hubble constant, the cold dark, or what is it, the lambda, the cold dark matter model, and all that stuff. That's where, after the fact, when they had different optics and they started discovering that there's more things in the sky emitting energy, and to explain that and fit it within their model, that started to fail, and they had to introduce new constants to explain things. That's where all that stuff comes from. It's not like they figured out that the mass of they figured out the missing mass of the universe. That's what it had to be to fill it in observationally, to keep everything else proportional and to keep it together. I mean, we're reading that book, about the redshift observations and, directly related to Hubble's constant and all that, and the belief and adherence associated with all that. And it's like, that's just based off some dude's interpretation, and Halton dared to have a different interpretation, and they were like, how dare you, and took away everything from that man.
How dare you? Yeah, I'm still
How dare you,
skeptical that you can determine the mass of something through looking at it.
Are you sure,
Oh,
man?
dude.
Did you drink enough Kool-Aid? Let me get you a robe, because that's definitely how we determine masses of all stellar objects. Always how we know. In fact, during my eclipse deep dive, if you look in Stellarium and you watch, say, an eclipse cycle, you'll see in the lower left-hand corner, if you're focused on the moon by hitting it or doing the square or whatever, it'll give you the data stream, and its mass is constantly fluctuating. And you're like, why? Why would its mass be constantly fluctuating? And it's like, oh, because the optical diameter is constantly fluctuating as it gets more or less obscured. And that's the most retarded thing that I've ever heard.
Oh yeah.
Well,
Right?
to be fair, it did work for my ex-girlfriend. I mean, it worked for me anyway.
Mass fluctuation?
No, I could determine the mass by just looking at it.
Oh, nice.
I mean, they weren't too far off with the concept, but it didn't really work in this scenario.
Historically has been problematic, let's just say. The trick is, it's like, hey, how do I give you, I'm going to tell you the mass of that thing in the sky. You'll never in a million lifetimes be able to confirm any aspect of this, nor will any of your descendants in living memory or history. But I'm going to tell you with a level of confidence that I know what that star weighs. That's a brilliant move. It's like, okay, cool, chief, cool story, right?
It's inherent in
Like-
everything in their mindset. Like just today, I heard on the news they were talking about a 1,000-year storm. And I'm like, okay, so you have weather that tracks back, maybe 700 years, weather tracking. Even if you could go back 1,000 years, that's not enough data to claim a 1,000-year storm, like a 1,000-year flooding or whatever. Like it just, the assertions inherent in everything in our everyday lives is really insane, especially once you start considering the fact that once you make one assertion like that, and then you start making other assertions alongside them, and you combine those assertions to then make, draw conclusions about things based, like you have multiple margins of failure built into your equations, and then those are compounded within your results, your result set, which would essentially be your model of the universe in this case. And so or with the case of what Shane's talking about. And so it's just essentially, when you're asserting all these things that are just guesses, and you have all these like variables that you're just kind of filling in with a best guess, you're completely into, what we would call fan fiction or lore. You're just making things up. It's just all a big fun story that, you're insanely precise, but it's just a bunch of false precision because it's precision about, or you can call it real precision about your fantasy land or whatever.
Consistent precision about a fantasy land. Yeah, you're consistently accurate at describing the contour of Superman's under ruse, right? But does that mean that Superman's flying across the sky? I can always guess with calculus the rate at which the area under that butt curve, but does that mean that he's flying? No, it doesn't. Anyway, this isn't strictly related, but I wanted to throw it in there as the meter. What do you think, Alan?
Oh, absolutely, man.
The meter.
So this goes right in tandem with once you have something established and you make a system, a unit of measurement as a ratio of that established system, well, everything's going to work in it accordingly. So yeah, it's directly related. Really
Crazy. It's crazy because they think this is one of the biggest ways they got us. They're like, go measure the world in any metric unit known to man. It's just units of a sphere, guys. It's like, we got you. That's a tough one, right? Because people are like, no, they changed it. And it's like, they changed nothing. They changed the historical contextualization of what they'd already done. That's all that changed. Everything is the same. It's exactly the same. As a matter of fact, let's see. Let's go to the other one. This one. Just because they say they ratioed it against a different thing, in this case the speed of light, and of course maintained by the constancy of the oscillation of cesium, doesn't mean that the actual value of the metric changed in the first place. It literally went from 39.37 inches to 39.37 inches to 39.37 inches, and they're like, nah, we changed it. And you're like, but changed it to what? And they're like, well, it just says that it's a ratio of it. And it's like, shut up. It's exactly the same thing. It's always been a proportion, a 1/10 millionth of a terrestrial meridian, meaning a meridian, of course, guys, meaning a bisecting great meridian means you have a sphere. If you have a meridian of anything, it's a sphere. If you have a bisecting meridian, it's a sphere. So a meridian, a terrestrial meridian, means a land sphere. Okay, so we're starting off with a definition of a land sphere, and we're trying to get the dimensions of it. And then we're like, you know what's best to measure dimensions of a land sphere? Well, proportionate ratioed units of a land sphere. So that's how they started. From the North Pole to the equator, they have ratioed that as a proportion of a meter. And then if you tell that to Globers, they're like, well, that sounds uncomfortable. I don't like the way that is. That's not what it is anymore, silly. Now it's ratioed against light speed. And again, same value. They just found a different threshold to ratio it against to make you think, though, now it's safe. Now it's a meter. And of course, a meter is used to get what? You got inches to miles. That's 2.54 centimeters to an inch. You got meters to kilometers. Then you got kilometers to miles, right? And then you got statute miles to nautical miles, which is 1.12 something like that. So all of it, right, is just ratioed to a meter. You're only counting things in various forms of a meter. And then if a meter is a portion of a terrestrial meridians, we're just counting things in little baby terrestrial meridian. Right? And then they're like, how come the distances always add up to a big terrestrial meridian? And you're like, well, I don't know. I got all these baby terrestrial meridians laying around, and I put them together to make a line. And then now it's a big daddy terrestrial meridian. Like, I don't know how it happened. But that's why I say all the distances are globe distances, right? But
little baby terrestrial meridians.
Widow to West Wheel meridians.
And then it's like, that's not a problem. And it's well, I mean, it is a huge problem, right? That's why I had to put the first slide in there, because I was like, Flat GPT, explain as if to a child why measuring things in units of a sphere is tough to prove sphericity. Right? Like, if this is the measure, then how do we differentiate? And literally it's like, okay, well, here, like, everything is in spherical coordinates, first of all, as I always say, longitude, latitude, and compared to the celestial sphere. So anything you point to, you're going to use that. But the main kicker is any distance measured in meters can directly be related to the spherical geometry of Earth. So, I mean, how come it always equals a sphere? Well, I have an inkling. right? And back to this one, right? So, yeah. What do you guys think about the meter and the terrestrial meridian?
Pretty fun, pretty crazy. Well, now it's also tied to the speed of light. Since like the 80s. So it's even more, the meter is wound up in all sorts of fun derivation at this point.
I mean, not really derivation. They just took, hey, what proportion over this would still equal the 39.37 inches that I know it has to be? And they give us that. And they were like, look, now it's ratioed against the speed of light. And they're like, well, how many terrestrial meridians equals 1 over 299,790,158? Oh, one. One. Okay, cool.
Nice. Nice and clean.
Like, that's the relationship. That's why I say, like, when they say they now ratioed against the speed of light, all they did was change the historical contextualization of the first ratio.
Which means that a meter is longer from east to west than it is
to south.
west
Yes,
to east.
sir.
Yeah.
Yeah. If they tied it, if they kept it to a terrestrial meridian, that wouldn't be the case, right? But wait, it's both. That's hilarious.
It's absurd.
It's absurd. Do we want to get to the big gravy, or do we want to let Piezo describe it?
I think he's still AFK. I was looking for, the story we're told about Eratosthenes, where did he do? Oh yeah. So the stadia, right? They're like, oh, Eratosthenes, estimated he was pretty close to getting the circumference of the Earth, and it's like, well, how'd they do that? Well, nobody knows what a stadia is, but a bunch of lads got together and agreed that a stadia would be a ratio of a terrestrial meridian, and oh my god,
No way.
so when they say that Eratosthenes guessed within 98% of accuracy, all that is that some dudes literally just picked a number that gave them 98% and was like, that's what a stadia is.
Yep.
That's all it took. It's not it's not like there's a historic record of like, oh yeah, dude, these guys figured out a stadia, they had a different system, but when you convert, no. They just agreed it's this system and imposed it on history.
This is how many baby terrestrial meridians we're gonna count it towards. I'm just gonna start calling meters baby terrestrial meridians.
That's there's no other way to really call it anything else now.
It's like, hey, how many baby terrestrial meridians is the equator on your flat Earth? It's like, well, it's kind of a loaded question. Oh, dude spent 3 hours asking me that today. I made him a meme. I wrote him a rap song, gave him a music video. I did a little anime. I did a GIF, wrote him in text, sent him like, dude, he asked the same all day. But how long is the equator on flat Earth? I'm like, good. Well, 2 pi r based on the graticule, meaning that you get what? 2 times the radius would be 3959, would be 2 times pi 3.14 times 3959 would give you 24,901, which would be statute miles with the circumference if you're doing optically, right? But that's just according to the graticule. And he doesn't take that, right? He just makes me say it over and over and over again. And then at the end, he's just like, sphere. It's like, but I addressed this immediately. Anyway.
I think Pizio might be gone for the night. He said he was only stopping by real quick for something.
Cool. You want to wing it then?
Let's see here. I mean, by you want to wing it. I'll trust fall into you doing it. Then yes, I'm definitely okay with that.
Cool. Still, have you seen this yet?
Nope.
So we have essentially, to our judgment, gauge the density of the etheric background. Right? And this is just pretty much the density of the medium, any medium, based on energy in a wave formula. Right? So this dastardly thing right here is what we're manipulating to shoot the density of wave propagation in the medium. And this would be a medium. Of course, we're saying the medium is the ether. So you got energy in joules, mass per unit length, wave speed, time, frequency, amplitude.
Okay. Back up to mu. Mass of what per unit length?
per unit length in kilograms per meter. What it
No,
says.
no,
That's
no,
supposed.
No?
Mass of what per unit length?
Was it tied to the Planck? Just says the mass, right? VT.
Yeah, the mass.
The mass.
What? Mass of what again?
Well, I
That
mean,
was supposed to be the density of the medium.
is it?
Yeah, so this was some wave equation for energy for
You're
whatever
actually
the
talking about the density of lines of force coming at us because of the ether? Is that it? Because there's no mass involved. It's
No.
an electromagnetic force. It's not. This is a misperception, as far as I can see so far.
shoot.
Oh,
See,
it was
we're
a bummer
talking
we
about
don't have
the
piezo. Let me
frequency
try
and
and.
amplitude
Did anyone try
of
pinging
a
piezo in
wave.
chat?
Yeah, I
But
tried.
this is paradoxical to assume that the wave has mass when it's transmitting through the medium of some other thing like physical space.
Well, the other one didn't have mass, Alan.
Well, it's not the mass of the wave. It was supposed to be the mass of it's a density equation for it's the energy equation for a wave propagating through a medium, like how much energy it would have based on those variables, right? But if you reverse it where you know the speed of light and you know the time and the hertz and the frequency and all that, then it would give you would be able to solve for mu. I don't know why I like wrote it messed up or whatever, but it's supposed to represent the medium that it's propagating through, give you the direct energy proportion, like how fast it can propagate through that medium.
Because we're just trying to find mass per volume, essentially density, right? So we need mass to start. What do we do here? Let's see. Mass. There's no mass here.
That's what I figured.
Yeah. So I don't know what happened there. So I bet.
Just
like,
checking.
there's no mass in the one that actually computed, dude. that I can recall. Let's see.
Yeah, it gives you the average density to allow electromagnetic propagation to maintain that frequency and speed.
Yep.
So, but not sure where all the math got lost in translation or whatever, but that's what it's supposed to represent.
That happens
They
a
use it
lot
for
when
other
people start
stuff.
to juggle formulae.
Yes.
You-
Formula jugulation.
I think this is directly from Piezo's homework, and he came in and was like, "Hey guys, guess what I have?" And we were like, "What? What is that? Let me see that."
Right down the path, Mr. White Bunny Rabbit.
Yeah, the calculation for and like essentially looking for if it's all pressure mediation and density, then you're looking for like what pounds per what kilojoules per square kilogram or something dispensation against density, which would be directly proportional to mass, which would be what measurement of literally the grip of ether torsion on the world or whatever electrostatics. So the mass per unit length of the ether mu is 2.2 times 10 to the negative 30. That's a pretty small number.
Yeah.
Yeah. Well, we were looking at Otsutovsky's numbers too. And being like his are really small too.
He's got some tiny numbers.
Yeah. Hugely like infinitesimal.
No, I would just call it a misperception and misattribution.
But he's defining
Until
it.
you can, I don't know, man. Until you can pin it on a tangible, you can't use tangible units to measure it like that. I'm kind of sounding rhetorical, but I would refer you back to how things went last night regarding the ether.
Word.
that it's a result. It is not an entity.
An entity. That's true. But like, as a tenuity rating of a background medium, it would have to have a value of some sort, which you should.
It has attributes. Yeah, you know, anything has properties, but physical presence is not a measurable aspect of it.
Because I don't even know what this is. -8 times 8.5 times 10 to the -12. That's that's the density.
Yeah, it's a negative density, just shy of nothing. It's just negative nothing, but only a teeny bit negative. Right?
Just shy of nothing.
Well, even in scientific notation, this number shouldn't be negative to my mind when we're
It's just a hair's width, even less than nothing.
we're measuring a fly on a hare's ass, but it's too big.
8 billionths of a kilometer per cubic meter of next to nothing because it's slightly less than that.
So what instrument do you use to register 8 millionths of a nothing? By the way,
That is a good question. Ether density.
yeah, an ether density
What's
gauge.
the tool? What is the tool?
It must just be calculated. You can't actually measure it.
I mean, what do I order
Oh,
at Amazon
vertical
that
ruler.
measures things in kilometers per cubic meter? And is there an Arduino module of it? Okay, I'm going to be back in about a minute and a half. One sec.
Were there any other constants in nature? I think it was Planck's constants, but those are just derivatives of the other constant, so nothing special. It's like once they have the basics, they can continue to make up all the other shit, right? Planck length, Planck time, Planck energy, Planck mass. It's just like, oh, well, Planck length, combination of the other constants, combination of the Planck constant, gravitational constant, let's be like. So different algebraic expressions there, different cubes, different functions, different curvature functions, but same thing. And then you just reinterpret it to be like, well, it actually represents the length of this, not necessarily a mass scale nonsense particle or whatever. So constants have value, and they've corrupted that value to support their nonsense physics, and that's what they needed, right? They've retconned the world to get real life constants to get things that aren't real to be substantiated, right? Mass and stellar objects get substantiated by big G, which is crazy. It's a derivation of little g and a torsion of two masses on Earth. And they're like, oh, you know what that means? How much that star weighs. 1-for-1 direct correlation.
You say it like that.
Trying to make it sound as logical as I can, but it's ridiculous. Well, that's pretty much it. That's a lot of math. A lot of math for tonight.
Who or what helped them figure out how the fuck to do that?
Right?
Good question, Alan.
I'll pretend to
that?
throw his voice down there by levelist.
What's up? What'd you say?
I practice ventriloquism.
That's really good.
Why does he have two mics hooked up? How does he do that?
So do we pick a topic that nobody gives a shit about, or nobody has any questions? Contents are kind of important. They built all of
I
physics
think
around.
that pretty much sums it up.
Yeah, there was that awesome video that Toby linked earlier. Can we watch that to play it out, or?
Ooh, that would be kind of
Yeah.
cool. That video is pretty good.
Yeah, that was awesome.
Yeah, let's watch that to play it out. That sounds great. Are you in Windows, Alan? Should I boot up?
I can do it. Where is it?
Shane, we can make Shane do it.
Nice.
I need both of you to sign an affidavit that Windows is superior in this instance.
No.
Nah, I got Miller's
Nah.
assistant.
Can't do it.
All right, you shoot me the link.
Affidavit, huh? Jesus.
Yeah, man.
Are you guys using Linux? I guess.
Yeah.
You talking about the superior OS, except for this instance in particular?
Does PC master race only apply to Windows PC or what?
Bro, I'm a Windows dude all day long.
All right, I'm back.
Welcome back.
Yo, we
Yeah.
were just about to watch a video to roll to essentially play things out here about Planck's constant and universal constants.
Planck's constant, sigma t to the fourth, is black body radiation constant.
Yes.
Yeah, actually.
Bitchin'.
Shout out to your boy Planck and his constants.
Your homeboy Planck.
Young Planck, they called him back in the day.
I think
Oh,
he went by
God.
Plankton to his boys.
I think that was
Only
the
if you knew
nickname
him,
he
though.
had.
Yeah, on
Right.
the download of the G's.
Something tells me this is part of the formulation of just exactly how they got to the figure for absolute zero in Kelvin.
One of the first gangsters.
We do like to follow those hunches.
Not to spoil it.
Morley's running some updates on his Discord. Give me just
Nice.
a second.
Oh, Shane said he would do it.
Yeah, I got it.
Oh, nice.
I was just
Could
only
you
kidding about the
imagine-
affidavit. I just need to sign email in blood if you could do that.
Could you imagine had Discord and like YouTube and shit? That'd be crazy.
I was waiting to download it because it looks chunky. There we go.
Oh, what up, Morley?
How you been, Moore? Out there measuring?
Who's Morley?
Mickelson's lab assistant, Miller's lab assistant,
Oh,
otherwise known as a true homie, a fellow periodicity measurer.
All right, there we go. I think I'm good. Streams up for me. Streams up for my stream.
I'm in there.
A little quick 8-minute, 10-minute, 12-minute, 15-minute video. Maybe we should put it up on speed. Now we can't.
I just
Good.
play it normal.
Everyone in it.
In a computer, the information you would need to enter is first all the laws
You
of
gotta
physics.
slide it back
The
a
initial-
little bit.
Oh,
It started.
If you wanted to simulate the universe in a computer, the information you would need to enter is first all the laws of physics, the initial conditions of the universe, and about 20.
did he just say you just got to put in all the Planck's constants? You got G constant, the
he's
big
like-
constant, and then you get
Oh
it
yeah,
right?
this guy says some hilarious stuff in this video, but
Okay.
Oh, you mean you want to simulate the astronomical universe? Because if you want to simulate the universe, you need the opinions of absolutely everybody who ever lived, and then you need to get the birth records, and then you need to file check with
That's
the
a crazy thing.
DMVs all over the universe, and then there's university records for all over the universe. Got to put those in there, and then there's the news headlines for the entire
University
history of the universe. You get those too, and put those into your computer, and then yeah, now you got some simulation going.
true.
Off to a great start. 9 seconds in. Everyone disagrees. Here we go.
26
And it
fundamental
all started
constants.
with a little assumption.
These constants are
Just one assumption, guys, and then 10 million more on top of that one.
needed in
It
order
came
to
from
describe
nothing,
the
go.
universe as best we know it. And if you did this and let the program run, you would end up with a universe which would pretty much look identical to what you see all around you. We're familiar with the laws of physics, but what are these 26 fundamental constants? These are constants that have to be measured and are what they are. There is no current theoretical basis to predict what these should be. The first
Whoa,
15
I
of
didn't
these
know
are the
that.
rest masses
Oh.
of the fundamental particles.
Dude, they got me again. I just assumed this stupid model had a theory, and they just like, nah, we're winging it, bro. We've been winging it. We wing it still.
Yeah, this guy's pretty good because he's pretty candid about everything.
Dude,
What do you-
no theory. Like literally, we have no freaking idea, but here's what it is. It is what it is.
What do you think he meant by no fundamental basis?
of the Standard Model. 6 quarks, 6 leptons, and 3 bosons. 4 of these numbers are the quark mixing parameters. These are required to describe the weak nuclear force and nuclear decay. Another 4 numbers are the neutrino mixing parameters. These describe how neutrinos mix with each other. There's the cosmological constant, which describes the amount of acceleration present in the universe's expansion. The fine structure constant, which represents the strength of the electromagnetic interaction. And finally, the strong coupling constant, which defines the strength of the strong nuclear force involved in keeping neutrons and protons glued together in the nuclei of atoms. But you'll notice that these constants all apply to some kind of object in the universe and how these objects interact with each other. They do not apply to all things everywhere. So perhaps they're not so fundamental in that sense. There are, however, 4 special constants that apply to everything everywhere. So these may be the most important numbers in the universe. And what these constants reveal about the universe is rather astonishing. What are these special constants, and what do they tell us about the universe in which we live? That's coming up right now. Before we get into the incredible story of the constants of the universe, let me tell you part of my inspiration for making this video. I watched an 8-episode series on Magellan TV, today's sponsor, called The Secrets of the Universe. This series looks at some of the strangest phenomena in the universe using some superb graphics and supercomputer simulations. Magellan is a new kind of streaming documentary service founded by filmmakers and producers who bring you the best documentary content. Featured subjects include history, nature, technology, and of course science. You can watch it on any of your devices, and if you enjoy 4K, you're going to love their library. Magellan has a special offer for Alvin Ashbears. If you click the link in the description, you'll get a free 1-month trial. If you want to support
Sounds
this
like
channel
digital propaganda on
Magellan
demand or
TV,
whatever for
then
a
be sure to
nominal
click the
fee.
link in the description. Consider the simplest atom, the hydrogen atom. It consists of 1 electron and 1 proton. To describe its interactions, at a minimum, you have to know a few of its properties. These would be properties such as the fundamental charge of the electron, the charge of the proton, the mass of the electron, the mass of the proton,
How about where it is?
and the strength of the
Nope, not
electromagnetic
necessary.
force.
Don't
These can
need
all
that.
be found from the fundamental constants. Fundamental constants means they are measured
Advanced
properties because
location.
we do not
Look at
currently
all the
have
stuff
a
we can infer
mathematical
without ever
model
actually
that
knowing where it
predicts
is.
exactly what these numbers would be. So
Little
these
bugger.
cannot be derived. They have to be measured. This is not to say that some mathematical model doesn't exist which could predict these numbers, but it does say that we currently do not know what such a theoretical model is. It is possible that a future theory of everything, perhaps something like string theory, would predict these
that'll
values.
probably do it.
Now, if we go back to the same hydrogen atom model, in order to model its behavior even more precisely, we would have to take a few other fundamental constants into account. The electron and proton, for example, have rest mass. Therefore, they would gravitationally attract each other proportional to the gravitational constant g. This gravitational constant appears in both Newtonian gravity and general relativity. It can be thought of as the proportionality factor between the strength of gravity and the masses creating that gravity. Since gravity applies to everything everywhere, g is the first of 4 constants that is universal. It has units of length cubed divided by mass times time squared. The electron and proton would attract each
There you
other
go.
proportional to the permittivity.
That's the equation we just had, but you can't get mass without little g anyway.
Perfectly relative to
Yep.
what you guys were showing earlier, yeah.
Of free space, epsilon naught, because this permittivity is the electric constant based on James Clerk Maxwell's equation.
This is going to be light speed, right? The light speed based on the properties of the vacuum.
Yep.
And
Yep,
since the
gravitational
electron
medium
is
density, for
spinning,
sure.
it would have a magnetic moment proportional to the permeability of free space, mu naught, because it is the magnetic constant, also according to Maxwell's equations. Mu naught and epsilon naught are properties of space and are constants that have to be measured. There's no theory that predicts their values. Turns out that mu naught and epsilon naught determine the maximum speed of light in the universe. This was found by James Clerk Maxwell as well. The speed of light is a very interesting constant. One way to think of it is as a conversion factor between mass and energy, as found by Albert Einstein in his famous equation E equals mc squared.
That's
But
a
it can
terrible way
also
to
be
think about
thought
it.
of as a
Nobody think about it
conversion
like that.
factor between the time dimension and the 3 spatial dimensions of our 4-dimensional universe. C also applies to everything everywhere and is the second of 4 universal constant. It has units of distance over time. Another constant which applies to everything is h, Planck's constant. It is the fundamental constant that sets the minimum scale of quantum phenomena. It can be found in just about any quantum mechanics equations, from Schrodinger's equation to the QED Lagrangian to the Dirac equation. It is associated with quantum states and transitions of quantum states. Planck's constant has units of mass times distance squared divided by time. Finally, there is Boltzmann's constant, which also applies to everything. It plays a role in determining the amount of vibrational energy contained in an atom related to temperature. It is just the definition of the energy contained in 1 degree Kelvin. It is in units of energy per degree. And using just 3 of the 4 constants, G, C, and H, we get some extraordinary insights into the nature of the universe. So for example, if we take these 3 constants and manipulate them mathematically like this.
Where'd that mass go, Meow?
Wait, globe, it's a globe, hold on.
We get a length.
If we
What
just
is this
algebra
length?
the
Well,
shit out of
this is the
all we
Planck
get
length.
left is length.
It is the minimum
time.
length that would be meaningful
So
in
look,
quantum
pause real quick.
mechanics.
We started with the constant from Big G from Cabin Fish, right? And then we have H from how much energy can exist over 1 second for Planck's constant. You don't have to rewind. It was.
Oh, I
was
got
just
it,
gonna
dude, I
do
got it.
Oh, you're good. Well,
So H is
now,
Planck.
now I lost track of what I was talking about, though.
I'm too good at it, come on, man.
Yeah. So anyway, just based off of those, right? They've, now they're going to tell you all the stuff about the universe. Anyway, continue. Or the speed of light squared or cubed.
Crossing
Sorry.
out of stuff again. I really liked when he crossed out stuff and reduced.
Yeah, like that
What's
mass.
that mass?
Yeah.
What's that mass disappear again, real quick?
Yeah.
Oh, ready?
And
Whoa,
keep
hold
in
on.
mind, so what I was showing earlier with the electron, right? When they were doing that experiment to get how much deviation they would get off the center, that's how they extrapolated how much mass would be needed when they ratioed it over, when they ratioed that energy over the radius of a sphere. Like with that assumed amount, then they could go, oh, okay, it must have weighed this much then to produce that deviation. So that's where they put mass into it. Like they've never weighed an electron or anything, right? They bring it in when it's convenient to make the prediction for the deflection, and then they take it out when they when they don't need it.
Yeah.
Yes.
Well, they can always squeeze something in and then square it a few times to make it all work.
Oh, you know what? I found Shane's constant, and when added to Alan's constant, that fixes all the problems. Actually. Oh, and we need another. Oh, you know what? There's a Toby constant, and we need that one too, and that fixes the new problem.
I'll get a constant one day.
Yeah.
Seeing how many things are assumed. Oh, go ahead. I think flat.
Well, this is the Planck length. It is the minimum length that would be meaningful in quantum mechanics. Similarly, by manipulating these constants mathematically,
Would the mask go meow? Oh.
we get time. What is this time? This is the Planck time. This is the minimum time that can exist that would be meaningful in quantum physics. We can also get energy by rearranging
It's
some
kind
of
of
these
like hammer
constants.
time.
Nice.
Hammer time.
This is the
I get
Planck
it.
energy.
But different.
This is the maximum energy that could be contained in a cube that had the size of 1 Planck length. We can convert this Planck energy into mass by using Einstein's famous equation, E equals mc squared. This represents the maximum mass that a cube of 1 Planck length could have. All these are values for the Planck scale. This scale really applies to everything in the universe. The units of these scales may be the most natural units for measuring things. Since these numbers are ubiquitous in physics, physicists often just use what's called natural units and set these 3 constants equal to 1. But
There
what
it
is the
is.
significance
There's
of
the
Planck scale?
integerization.
The Planck length is the
Boom.
shortest length
Integerization
that
of
means anything in the
physics.
equations of quantum mechanics. This is not to say that something smaller doesn't exist. For example, the singularity at the center of a black hole is supposed to be an infinitely small point with infinite mass density. But Planck length is the smallest unit that we can measure. It is the smallest scale that we can theoretically probe with particle accelerators. These scales are the theoretical limit, but in fact, it is many orders of magnitude smaller than what we can practically measure today with the most powerful accelerators like the Large Hadron Collider. The Planck length is fundamental. So for example, if string theory is true, then the strings would presumably be as small as the Planck length. Any smaller, and they could not be defined in physics. This would also be the smallest size of the loops in loop quantum gravity. And these strings would vibrate at minimum time
10
scales
to
of
the
the Planck
negative
time.
99,
In loop
because
quantum
our
gravity, the
calculator won't
movement
go
of the
any
spin
smaller
network
than that.
would occur like
Without
a
its
digital
same
clock
boobs or
in
whatever.
increments of Planck time. Planck time is the time it takes for light to travel one Planck length. It is the smallest measurement of time that has any meaning in quantum mechanics. Planck time is the closest time to the beginning of the universe, occurring right after the Big Bang, that we could theoretically model.
Did you guys
This
like
would be
how
around the
it
time
also
that all
supports
four
all our other
fundamental
bullshit
forces
theories
were-
without substantiation simultaneously or whatever?
Gravity separated out and became a distinct force from the other three. We have no idea what occurred prior to this time, nor do we have any model for what could have occurred. Using the word before may in fact be meaningless because time itself started at this point.
It's
This
about
would be the
here-ish.
true beginning of creation. Even though we have no model for what occurred or what may
I
exist
love
at
a good
scales smaller than the
paradox.
Planck scale, many people, including scientists, speculate what that could be. For example, it could be a kind of quantum foam where gravity could fluctuate or be in superposition. Perhaps this is where gravity and quantum mechanics unite somehow. Or it is possible
Just don't say ether.
that space-time itself is quantized at this level.
Good.
And there is nothing
Quantized
smaller.
space-time.
Could
That's much better.
space-time be in superposition like other quantum phenomena?
Need more discontinuous
Perhaps,
dots and
but
flux.
this would violate some of the current understanding of gravity. Quantization of space-time at these scales is the kind of universe that the theory of loop quantum gravity implies. What about Planck energy? If the Planck energy was confined to the volume of a cube the size of one Planck length, it would form a black hole. The Planck mass is considered the smallest possible mass that a black hole could have. If we could create a
neat
black
metric
hole like
to know
this
for
in a particle
absolute certainty,
accelerator, it would
We
have
could just make a
gravitational
black
effects
hole.
at the quantum scale, and we could perhaps crack the holy grail of physics by understanding how gravity works at quantum scales, and finally come up with a theory of quantum gravity. If we actually built an accelerator that achieved the Planck energy for a particle like
This
an
is
electron, a
nothing
black
more
hole
than
would form.
nerd
So it would not help to
porn.
go to higher energies than
Yeah,
that,
at this point.
since the
But
black hole
first
would
part
just
was
get bigger, and there would be no information that we could attain. This is why the Planck length is
Well,
the smallest length scale that we
Like
could
Toby was saying,
theoretically probe.
though, gets
Note
into
that
that
Planck
fan
energy
fiction, right? Because once you've got
converted
these
to Planck
constants,
mass
I
is
mean,
really a
like
lot
George
of
W.
mass
Bush
packed
Sr.
into a very
said,
small
don't let
space.
a good
This is
constant
why
go to
our
waste.
the mass is
That's a
But
direct
Alan,
quote.
could you even be constant? Because I mean, the Planks are very.
Like, why stop there when you could establish the smallest units possible? I mean, think about it too, because these people have established their philosophy on getting there first, right? So they got to establish the smallest amount of energy, the smallest amount of distance, time, etc., and go from there to cover it.
And once you're like, look, we've done it, we've measured the smallest amount of anything, you're like, oh, see how the smallest amount of anything also applies to my crazy fictitious string theory world where everything's made of bubbles. It also applies to my Lego world where everything's made of Legos. This is the smallest Lego you can now have. And also applies to my galaxy string theory button winner where everything's a button, right? That's the smallest button you can have. And it's like, oh, that just, you stacked up a bunch of nothing on more nothing and it just farted. Like, okay, cool. Great.
Weakest force in the universe. It's
Or we
10 to the
rewind it a little
39
bit
times
and
weaker
play it back because I was
energy
kind of talking
terms. In
over it.
fact, scale that we could theoretically probe. Note that Planck energy converted to Planck mass is really a lot of mass packed into a very small space. This is why black holes form. The mass is equivalent to about 1% the size of a mosquito. Although this sounds really small, it's really large in energy terms. In fact, this mass converted to energy is equivalent to the energy contained in a tank of gasoline or petrol in your car. When you pack that much energy or equivalent mass to a size as small as the Planck cube, you get a black hole. This is a pretty large amount of mass for such a small volume. Why is this the case? You have to
Bada
remember
bing,
how
bada
weak gravity
bang.
is.
You got a
It's
black
the
hole.
weakest force in the universe. It's
You just gotta
10 to
take
the
this much
39
mass
times
and this
weaker
much size.
than electromagnetism,
Boom,
for
black
example.
hole. Instant
And
formula.
because it's so weak, we have to pack a lot of mass for the gravity to be strong enough to form a black hole within that volume. Now, some people have used the precision of the various constants to argue for fine-tuning. This is the claim that conditions which allow life in the universe lie within such a narrow razor's edge that any slight variation would
all
result
the
in
constants
conditions
happen to work
which
out
would
like that
either not
because
have created matter
reasons.
or large astronomical structures like solar systems or complex
How
compounds
did we get with
or
that?
life as we know it. And some argue that the chances
Definitely
are so
not
small
God, dude.
that
But
they must
what are the
be
like? What a random chance! Are we lucky, bro?
precise constants were entered into the program, or that a supernatural being, God,
There we
must
go.
have chosen the constants so that life could exist.
There we go.
Others counter this argument by saying that the universe isn't all that fine-tuned for life because, by all accounts, almost all the volume of the universe supports no life. There's only a limited number of planets and a limited number of solar systems that are within limited distances from their stars with specific combinations of compounds, namely carbon and water, that are conducive to life as we know it. But if you look at the vast number of planets available in the universe that nature has to work with, there's bound to be life on some of them. Or that the constants are but one variation in a vast multiverse of universes.
That's a lot of bowls.
And life in a different form
Look
could
at how
exist with a
insane we
different
are.
set of constants.
We look up at
None
the
of these
sky,
claims
we're
is
like,
currently
you
falsifiable.
couldn't even
Any way you
exist
look
as
at
a
it,
human
I
based
think
on
we
your
have won the
periodicity.
cosmic lottery. The question is, how many
What?
tickets did you
Dude, the
buy?
parallax angle of
And how
that
many
star compared to when I know the
simulations
sun
did our
is and how
overlords
big I
create?
guess Venus is actually
I'd like to
means
thank my
that you're a
generous supporters on
bajillion.
YouTube and Patreon. If you like my videos, consider joining them.
That's enough, right?
Shout
He's
out to
done?
you, boy. Yeah, that was a good video.
It was. It was very good.
Yeah, once the rules have been established, you're welcome to play Dungeons and Dragons, man. You can even become a dungeon master. But should you choose to deviate from that and try to establish your own lore, you will be swiftly dealt with.
No lore for you. Yeah, not allowed. Dude, the first thing they threw up was this one, right? It was like, oh, well, actually, it didn't say it was the speed of light. It ended up being the speed of light through like a dramatic reveal, right? But we knew what it was beforehand. And it's like, oh, it turns out all the properties of the thing that you think is real is just determined by the properties of the thing that it is in. So, like, the background medium. The
What a
measurements.
precarious position to be in.
The properties of the medium itself actually is what determines the speed of light. So what does that tell you? Is the speed of light relevant? Absolutely. Does it mean that that light beam is traveling at a rate? Fuck no. Fuck no. This is a quantifiable rate of induction, testifiable metric, right? It's metric, it's used, it's real. They just told you that it was, if you're like, so like if you have an experiment and you're riding a light beam like a cowboy from the center of that light beam and you're riding yeehaw and you're going around the universe, then this is actually the max speed that anyone can go, especially if you're only relative from yourself or whatever. I can't actually make
There
the
you
light
have
beam
it.
work, but I can give you the math that if you were on that light beam, how it would look. Einstein in a nutshell.
What it would look like from a null geodesic. Outstanding.
I really like that presentation, guys. Learned a lot about constants tonight.
So that was constants. Yep. That's about it. Short one tonight. Well, a short one compared to the double dodecker 302.
Toby, I woke up this morning and I didn't have any coffee. Where can I go to get some?
Coffee.
Is there a place? Do you know a guy who deals in coffee in large quantities? Perhaps let me lay out a situation for you. I'm a busy guy, right? I'm reading PDFs all the time and typing on the internet and whatnot, right?
Twitter
I
trolling
don't
or
have
whatever.
I don't have time to go to the store. I don't have time to do anything. But if there was like a website I could go to, and I could subscribe to, if I could just say, here's my money, you send me coffee on like a schedule. Is that a situation that could be arranged? Like, do you know anyone that could facilitate that?
Yeah, I do. I do actually know someone that. Well, actually, it's funny. It's funny that you should ask that because I happen to roast coffee, Alan. What? I don't know. Yeah. I don't know how you came up with that question, but yeah, I don't know, man. You seem to be. I don't know. There's some synchronicity going on, right? Because I happen to run a coffee roasting company called Brushtail Coffee. And it's, me and a grill and a special drum contraption. And I just, I order beans from a couple of third parties, and I, work with different processing, or they work with different processing facilities. And, I pick what I like and I roast it. And if you order coffee from Brushtail Coffee, it will be roasted to order. So you're not going to get coffee that's been sitting around or that's, a certain batch from whatever day that I'm going to, throw into your shipment and ship it off to you. No, you'll notice I have multiple different types of coffee. And if you pick one and order it, it will be roasted to order and it will be shipped within the day, typically within 24 hours of when it was roasted. That's generally the latest it would go. And that way it will get to you, within 4 or 5 days at the most. And that way you can have coffee within the week it was roasted. Sometimes sooner than that even. But in any case, coffee is definitely noticeably better within the first 2 weeks essentially. And then it kind of starts to slowly taper off after that. If you buy your coffee at the grocery store and it has a best buy date, like an expiration date, instead of a roasted on date, then you don't even know when it was roasted. And that's a totally different metric to date your coffee by. So if you want to try fresh coffee, head over to brushtailcoffee.com or brushtail.coffee, BRUSHTAIL.coffee. So yeah, thanks everybody.
That sounds too good to be true. I've heard a lot of these coffee companies allegedly could use baby penguins in their mixtures. Are you giving me assurance that your coffee doesn't use any baby penguins?
We've actually walked back our claim on that because, some legal issues. So, there may or may not be, let's just, no one really.
Listen, guys, we have a new marketing campaign. There was an issue going on, like Toby said. We were deceived by our marketing manager. That person's been let go. The new PR manager is about to release the new campaign.
The new scapegoat's here. New marketing manager.
Exactly. Exactly. So what we have here is, I was watching an episode of Alex Jones, InfoWars, and he was saying that he read a study that if you drink coffee that isn't home brewed from Brushtail Coffee, it'll actually make you gay.
Oh, that has merit. I heard about the frogs. So
That's good to know. Yeah,
that may or may not be. That's a superposition of truth. And yeah. So there you go. Wow.
That's good to know. That's science.
All this talk about coffee made me thirsty. I literally had to go buy some Brushtail coffee. So
Wait,
Brushtail Coffee.
Toby, are you saying there's no baby penguins in your coffee?
No. That's what I'm not saying that anymore.
What? Okay, you know what? I'm gonna cancel my order. I thought I was getting ground baby penguins. So please,
no, you are. You are.
No,
order.
Alan. No, she may or may not be.
Wait,
just cancel my
for
order
legal
of
reasons.
30 pounds.
Oh, today's opposite day. I see what you're doing, Lily. Thank you. We'll cancel that order right away. Toby's not firing up the grill right now
and pulling out the extra beaks.
Dude, I ran out of coffee like 3 days ago, and I went to the store and I bought Maxwell, which is full of baby penguin beak, as far as I can tell from the taste and the texture. Now that I've been on Brushtail, so I immediately want to just throw up, and that's why I bought coffee just now. Anyway,
yeah, I was looking at Folgers, and based on observation alone, I can see.
Jesus.
I could tell.
All right, we're wrapping up, lads. Thanks for coming out.
We'll
see you on Thursday for the community chill sesh on Twitter Spaces. Looking forward to it, lads. And then, of course, Friday will be Flat Earth Fridays. See
thanks
you
for tuning in, everybody. Take care.